Hello.
No. Yes, please go ahead.
Sir, we didn't cover the topics that are given in the tutorial in class.
No, we have already covered. We have covered till that point. Yes, except LMTD we have not covered, but that anyway I have talked about in the last class. Okay. So what is been given in the problem 1 of tutorial 5 is I'll just go through the statement. An oil with a thermal conductivity of 0.138 watt per meter degree Celsius flowing through a 25 radius pipe exchanges heat with an external medium. At a particular section of the pipe, the radial velocity and the temperature distribution in the oil are V is given as 0.5 minus 800 R square, whereas temperature is given as 60 plus 1.728 into 10 raised to the power 5 R square minus 3.072 into 10 raised to the power 6 R cube, where V is in meter per second, R is in meter, and T is in degree Celsius. Determine whether the oil is in laminar or in turbulent flow. The second part is the oil being heated or cooled. Part C is calculate the average velocity of the oil. Part D is calculate the cup mixing temperature of the oil at the given section. Find the local wall heat flux, heat transfer coefficient, and Nusselt number. Okay. So am I audible and this white screen is visible to everyone?
Yes, sir.
Okay. So now what is been given is, let me just write down. This tutorial is going to take more than 1 hour, so we are starting early. Okay, so what has been given here is radius r naught is given. Radius r naught is given, so that is given as 25 is given, so that can be written as 0.025 meter. Again, what is been given is velocity is given as 0.5 minus 800 r square, and temperature is given, temperature distribution is given, that is 60 plus 1.728 into 10 raised to the power 5 r square minus 3.072 into 10 raised to the power 6 r cube. Okay, so this is what is been given. Now part A is what we have to find out is whether the flow is laminar or not. So whether the flow is laminar or not, that we have to determine. Now in this particular problem, what is been given is velocity V is a function of r square, isn't it? So when we look at the laminar flow, the velocity is a function of r square, isn't it? So that's the first indication that it's a laminar flow. If you look at the turbulent flow, it is velocity is related to r raised to the power 1 by 7, isn't it? Something like that is the relation. But let us look at this particular relation in more detail, whether it is fitting properly or not. Okay, so here what is been given is V is given as 0.5 minus 800 r square. So we can rearrange this equation carefully. So that becomes 1 minus 1600 r square, isn't it? And this we can further rearrange as 0.5 1 minus r by 0.025 square, isn't it? Something like this, correct? So this is nothing but what? This is nothing but 0.5 in the bracket 1 minus r by r naught square, isn't it? So if you take the square of 0.025 and inverse it, that is going to give you 1600, isn't it? So that's a clearly fitting in this particular equation. So this equation is a standard equation of a laminar flow. So where V can be represented as V max. If you look at the expression, something like this is the expression you are expected to get for a laminar flow, isn't it? So this is a clear indication that the flow is laminar. Flow is laminar. Is it clear to everyone?
Yes, sir.
So where Vmax is 0.5. Okay. Now in part B, what is being asked in part B, we have to find out whether the oil is being heated or being cooled, isn't it? So the temperature is given here, whether oil is being heated or cooled. That is what the question is, isn't it? So how we can, go ahead with in this case, we can find out easily because the temperature distribution is already given here. We can find out the temperature at r equals to 0. We can find out the temperature at r equals to r naught and check the value of temperatures, isn't it? If the temperature at r equals to r naught is greater than temperature at r equals to 0, then it's a clear indication that the wall which is there is at a higher temperature compared to the fluid which is flowing inside the pipe. So that's a clear indication that the oil is being heated. If the reverse is there, then it's an indication that the oil is being cooled. Another way of finding is we can find out dt by dr. We can find out dt by dr and we can find out dt by dr at r equals to r naught. And if this comes out to be positive, it's a clear indication that as r increases, my oil temperature is increasing. So that means the oil is being heated. If it is negative, then it's an indication that the oil is being cooled. Okay, so we will go with a first method. Okay, so let us find out.
Sir,
Yes, please go ahead.
sir, cannot we just simply check if we find what is dt by dr as a function of r, and then we can check whether it is negative or positive in the interval
Yes,
from
but
0 to
see, if you
0.025.
find out dt by dr, you will have a function of r.
Yes,
that
sir.
will be a function of r. So you cannot find out unless you put the value of r there, isn't it?
No,
So
sir. What
you
I'm
can
trying to
consider
say
r
is
being a
it was
positive
a
value and then you can conclude. Yes, yes.
it was a quadratic equation basically. So we found the roots of that equation. So we can easily check like the value of r of the pipe comes out to be between the roots. So the function dt by dr will actually be negative in the whole
Yes.
equation.
I'm saying yes, absolutely correct. You can find out in that way also. And there is another way of doing it is directly finding the value of temperature. Yes, I am agreeing on you on whatever the point you are making.
So can you please repeat the gradient point again? How to judge if
Just,
we are...
just wait. Just wait. So this is the equation, isn't it? This is the equation of the temperature distribution, isn't it? We can find out dt by dr from this by differentiating this equation, isn't it? And then at two locations, at least at r equals to 0 and at least at r equals to r naught, we can find out the exact value of dt by dr.
Yes, sir.
Isn't it? So at any two location, you find out dt by dr. If that dt by dr comes out to be a positive value, it means what? temperature is increasing with R. That is what it means, isn't it?
Yes, sir.
So if you are getting a positive value, that means it's a temperature is increasing with R. When we will have this type of situation, we will have this type of situation only when the temperature of the wall is higher than the temperature of the fluid, isn't it? Then and then only my temperature will keep on increasing from 0 if I move from radius R equals to 0 to R, isn't it? Still not able to get it?
No, sir.
This is the pipe. This R equals to 0. As I move along this direction, isn't it? As I move along this direction, if the oil is being heated, my temperature here, TW, should be greater than the T here, isn't it?
All right, sir. Got it. Got it.
Isn't it? So this can be obtained only if you are getting dt by dr equals to is greater than 0. Isn't it? Then and then only you can conclude that as you are moving along the direction of R, your temperature is increasing. Clear? So
Yes.
we will do it in a different way. So let's find out T at R equals to 0. So what we get is 60 plus 1.728 into 10 raised to power 5. So this becomes 0. So all I will don't have to write all these things. So what you are going to get is 60 degrees Celsius, isn't it? These two terms are going to become 0. Correct? And similarly, T at R equals to R naught, that you can find out directly by putting the value 61.728 into 10 raised to power 5 into 0.025 square minus 3.072 into 10 raised to power 6 into 0.025 cube, isn't it? So the value you are expected to get from this is T at R equals to R naught comes out to be 120 degrees Celsius. Just check whether this is correct.
Yes, sir.
So since this T at R equals to R naught is what? This is TW, isn't it? This is the nothing but the temperature at the wall. So clearly oil is being heated. So this is the answer of second part. So we can conclude from this as the oil is being heated. Correct? Let us move to the part C. In part C, what has been asked is we have to calculate the average velocity, isn't it? So average velocity we have to calculate. So average velocity, if you remember your fluid mechanics, average velocity is nothing but Vmax by 2. Vmax we have already calculated, that is 0.5 divided by 2. So it comes around 0.125 meter per second. Correct? So this is the answer of part C. Is it all right? Are you all able to get it what we are doing?
Yes, sir.
Yes.
Okay. So now let us move to part D. In part D, what we have to calculate is we have to calculate a cup mixing temperature. Cup mixing temperature. So what is cup mixing temperature? Cup mixing temperature is nothing but a bulk temperature. Okay. Cup mixing temperature is a bulk temperature. In other word, that is defined as a bulk temperature. So T cup mixing is defined as, it is defined as 0 to R naught, rho Cp 2 pi R VDR T divided by 0 to R naught rho Cp 2 pi R VDR. Okay, so what this equation is, this equation basically gives me an average temperature, averaged over energy. This equation gives me the averaged over energy. Okay, so this is a standard equation of the cup mixing temperature, which is basically gives me an average temperature, and this temperature is averaged over energy across the cross section of the pipe. Again, here the effect of the velocity is also included. Here you can see RV and T, this V here is a function of R, isn't it? And similarly, T is also a function of R, correct? So this is basically a averaged over energy. This cup mixing temperature is the averaged across the cross section with respect to energy. Okay, now in our case, we can put all the values based on what we are having. This is also called as a bulk temperature. This is also called as a bulk temperature. Okay.
Hello, sir.
Yes, please go ahead.
Sir, we haven't done this in class yet. This is under the laminar flow in a tube, and we did not cover this.
That I have written it later, but I am giving you directly here. It doesn't matter. It's just an equation, isn't it? And I'm giving you a perspective why we are using this equation. So remember, in the last class, we have looked at how to calculate the average value of heat transfer coefficient, isn't it? Where we have averaged over the length, correct?
Yes,
so in a
sir.
similar manner, here the temperature we are finding out, which is averaged over energy. So I'm giving the perspective. It's not that I'm not giving. So for example, if you are having this cross section where this velocity is varying, something like this, isn't it? And also the temperature is varying. So here temperature is TW, here the temperature is let's say T naught. So TW and T naught both are different. So there is a variation in the temperature also. Okay, but we wanted to have a average value of temperature which will represent this entire thing. So that is being calculated based on this cup mixing temperature. Okay, it's all right.
Yes.
Sir, what does this temperature signify?
This is a bulk temperature. If you wanted to calculate, let's say the difference in the temperature and the heat transfer based on this, you can directly use the instead of this laminar flow, let's say if you are having a turbulent flow. Okay, in a turbulent flow, how you are going to apply a Newton's law of cooling? HA delta T. So what is delta T there? Delta T is nothing but wall temperature minus bulk temperature. In a laminar flow, this cup mixing temperature has no, it's not used at all in the laminar flow, because in the laminar flow we are assuming that the resistance is lying till this point. But in a turbulent flow, the velocity profile is something like this, isn't it? So between this, mostly the velocity is constant. V is constant, isn't it? And also the temperature will be also similar to this, isn't it? So very small region, in this particular region, V is varying as well as temperature is varying, T is varying. So in turbulent flow, so this is in turbulent flow. Okay, so this concept of cup mixing temperature becomes important in turbulent flow. This becomes important in turbulent flow, but here we are just calculating for sake of calculating. We are not using it later on. Okay, but we are just calculating for the sake of calculation, because the calculation becomes easy because the velocity distribution we know, temperature distribution we know. So we can calculate analytically. The bulk temperature we can calculate here analytically, which is not possible in a turbulent flow. In a turbulent flow, we can only find out this bulk temperature by measuring. Okay. So why? Because the variation in temperature as well as the velocity will be lying only in this small region, and in such cases Q will be given as HA TW minus T bulk or T cup mixing. So this will be same as T cup mixing. Sorry. Okay, so this concept is used for turbulent flow, but just for a sake of understanding, we are calculating it because calculation can be possible in a laminar flow in an analytical manner. So we can calculate it in an analytical way in case of laminar flow. That's it. That is why we are just calculating it, but we are not going to use it later on. Okay, it's all right. Does it make sense? Hello?
Sir, if we
Why
are
not just
calculating the average temperature, then why are we including the velocity in it?
Same question.
Why we are so that is what I see. I said that see, okay. So in this case, remember the temperature profile will not only depend on the how it is varying across the pipe, but it also varies based on the velocity. It is going to be varying with respect to velocity as well. Okay, clear? So effect of velocity will also have there on the temperature, isn't it?
But temperature is given as a function of R only, so just calculate.
Velocity is also given as a function of R, isn't it? And that we are dividing it. We are dividing this entire factor here, isn't it? So we are averaging. It's not that we are not, see, if I put it VDR and if I don't divide it, then it's not correct, but I'm dividing. So I'm averaging it over even the change in the velocity. Not only with respect to the change in the R, but also I am, averaging over the change in the velocity. Is it clear? Actually, I should use the variation of rho Cp, and this rho Cp also should be used how it varies with respect to temperature. But that anyway we are assuming that it is constant. Otherwise, I would have used the variation of this factor also here. Still not clear? Hello? It is still not clear? Okay, so I am giving you another perspective. Okay. Remember, in the starting of this particular class, we said that the temperature profile in the convective flow will be dependent on what are the different quantities on which it will be dependent on. It will be dependent on density, specific heat. It will be dependent on thermal conductivity. It will be dependent on velocity profile, isn't it? That is what we have, said in the starting. Correct. Now I wanted to find out the cup mixing temperature, which includes the effect of all these variations. So what I'm doing here is, in a way, the cup mixing temperature is a temperature which is averaged over the variation of all these quantities. Now in this particular case, we are assuming that rho and Cp is not changing, but velocity is changing, and that is why the variation in the velocity I have included. Okay, but all other I can get it, that can be will get cancelled out. Is it clear now?
Yes, sir.
So I am averaging with respect to the variation in all the quantities, not just the velocity, but also rho, Cp, etc. Okay. Okay, so let us put the equation for velocity as well as temperature in this equation. So what we can get here is, just wait. So TCP can be written as 0.025. Rho Cp will get cancelled out. 2 pi will also get cancelled out. So R is a variable here. So R will remain as it is. So R into V. V is given as 1 minus. V is given as. So what we will get is 1 minus 1600 R square, and T we are going to have as 60 plus 1.728 into 10 raised to power 5 R square minus 3.7 3.07 2 into 10 raised to power 6 R cube into dr, and this is divided by again 0 to 0.025 R into 1 minus 1600 R square dr. Okay, so calculate this integral and find out the values. Calculate this integral and find out the value of this cup mixing temperature. So there is a factor of 0.5 here, but that will get cancelled out anyway. The numerator and denominator will get both will have that factor of 0.5, so that will get cancelled out. Okay. So anybody, if you are having some, high-tech calculator, you can calculate the integral directly. So calculate using the calculator and find out what is the value. You are expected to get around, I'm not sure whether this is correct or not, but check whether this is indeed the correct answer. Are you all getting the same?
So 1 minute we are doing.
So is it correct? Anybody?
Hello, sir.
Yes, please go ahead.
Sir, getting 85.024.
That's okay. That's perfectly all right. So this value is correct.
Yes, sir.
Okay. So we can go ahead with the next part. So let us move to the next part. Let me just scroll up a little bit. So next part is we have to calculate the local wall heat flux, isn't it? So next part is we have to calculate local wall heat flux. So local wall heat flux will be what? K dt by dr at r equals to r naught, isn't it? When we are saying wall heat flux means that will be at r equals to r naught, isn't it? And heat flux is defined as k dt by dr, isn't it? So dt by dr we can calculate directly, so we can differentiate it. So k into differentiation of the temperature expression, that is going to be I'll just scroll a little bit down and then we can do it. Okay, so that is one. Okay, sorry. Okay, so this is going to be 1.70. What is the equation? Let me just look at the equation. The equation is 1.728 into 10 raised to power 5 into 2 into r. That is going to be the first factor minus 3.072 into 10 raised to power 6 into 2 into into 3 into r square. Correct? Is it correct? And that has to be calculated at r equals to 0.025. So what is the value of local wall heat flux? Can anybody calculate it? So this
Sir,
comes around.
wouldn't the flux be minus k dt by dr?
Here wall is at a higher temperature, isn't it?
Okay, sir.
And the temperature at the r equals to 0 is lower. So as you move along the r direction, dt by dr is a positive quantity. So that negative sign is not required. So as you move along the r, your temperature is increasing. So that negative sign is not required, isn't it? Did you get it?
Yes, sir.
Okay. So you can put the values here. Remember, when we use the negative sign, we use the negative sign when as we move along the r, if the temperature is decreasing, then we use a negative sign. Otherwise, we don't use the negative sign. So in this case, the K is already given 0.138. So I just 138 into, if you put all these values here, what you are expected to get here is in the bracket. The value what you are expected to get is 2.88. 2.88 into 10 raised to the power 3. Just check whether this is correct.
Yes, sir.
So this becomes 397.4 watt, isn't it? Now, what is the second part in the last part E? We have to calculate the heat transfer coefficient. So heat transfer coefficient is given as heat transfer. So heat transfer coefficient in this case is defined as what? Heat flux divided by temperature driving force, isn't it? Temperature driving force. So that we can write directly as heat flux in this case is going to be Q, isn't it? Heat flux is Q at, and here delta T. So
T wall minus T bulk.
correct. So this is the equation, correct. So what we can write down here is 397.4 is the heat flux which we have obtained. Delta T in this case is going to be TW minus
T bulk.
T bulk has to be used only in the case of turbulent flow. That is why I said this concept of bulk temperature has to be used in the turbulent. I will come to this, just wait. Okay. So this is a very important point to note down. So this becomes 120 minus 60. So this comes around 6.624 watt per meter square degree Celsius. That is what you are expected to get, isn't it? Okay. Now coming back to this, why we have used here T naught and not T bulk? That is the question, correct? Remember, in case of a laminar flow, we assume that this entire thickness which is there in a laminar region, that entire thickness is used as a resistance, isn't it? It's not that the resistance is only present very close to the wall. In case of turbulent flow, we assume that the resistance is the maximum resistance offered to the heat transfer is only present very near to the wall, where the flow is mostly remains in the laminar region. So there, in case of the turbulent flow, this delta T has to be TW minus T bulk. But in case of laminar flow, it has to be TW minus T naught, because this laminar region is starting from R equals to 0 to R equals to RW. R naught. Okay. हेलो, हाँ विशेष जी बोलिए. हाँ, मैं अभी आने वाला हूँ थोड़ी देर में. ठीक है. ठीक है, मैं अभी आऊंगा तब साइन कर दूंगा. हाँ, मैं अभी आने वाला हूँ बस 10-15 मिनट में. ओके, चलिए. Okay. So in case of a turbulent flow, remember here in this pipe, I'll just draw it. In this pipe, when the flow is laminar, this entire region act as a film. In case of laminar, and therefore this delta T is going to be what? TW minus T naught. Correct. But in case of turbulent flow, very thin film of laminar flow is present here. So the resistance is present only in this layer. In this case, delta T is nothing but TW, and this entire thing is represented by a cup mixing temperature or a bulk temperature, TB minus TB. Is it clear to everyone what we are saying? Is it clear? Hello, am I audible?
Yes, sir. Yes.
Okay, so heat transfer coefficient will be given by this 6.624. Is a correct answer? Is it a correct answer?
Yes, sir.
Yes, sir.
Now we can calculate a last part, that is Nusselt number, which is given as HD by K. So H we have already calculated, that is 6.624 into diameter we already know. So 2 into 0.025 is the diameter. By K is we already know that, which is given in the problem, 138. So you can calculate the Nusselt number, which comes out to be 2.4. Okay. Is it okay to everyone? Can we go ahead with the next problem?
Yes, sir.
Okay. So the next problem, again I am copying the problem statement directly here. Okay. In the second problem, what is been given is, I will just go through the statement. Mercury is purified by a distillation, is cooled by passing it through a double pipe heat exchanger. Inner tube is 13.5 mm ID. The thickness of the tube is, inner pipe is 2.75 mm. The outer pipe diameter is 41 mm internal diameter. The inner tube of exchanger carries mercury flowing at a rate of 1500 kg per hour, entering at 250 degrees Celsius and leaving at 40 degrees Celsius. Cooling water enters the outer pipe at 26 degrees Celsius and leaving at 40 degrees Celsius. Calculate the required length of the tube. The following physical property values of mercury at the average temperature may be used. Okay, so what is been given here is, I am just drawing it schematically so that you know you will be able to visualize what is happening here in this case. So this is the inner pipe, and then there is a outer pipe. Okay, again, so this is what happening. Just wait, let me just do it little bit in a better manner. Okay. Okay, so this is what happening. So the inlet is mercury at the temperature of 250. So T 250 degrees Celsius is the temperature here. Outlet here is at 40 degrees Celsius. There is a water in temperature is 26 degrees Celsius, and water out is at 40 degrees Celsius. So this is at 40 degrees Celsius. Again, flow rate of the mercury is given, so that is m dot is given, mercury is given. So let us that is given as 1500 kg per hour is given. Okay. Again, this diameter is given. This diameter is 13.5 mm. Okay. Again, what is been given is this thickness. This thickness is given, which is nothing but 2.75 mm is given. Again, the outer diameter, this diameter is given, which is 41 mm. Okay. So this is the information given to us, correct? Now what we have to find out is how much length is required in this case. What we have to find out is what length, this particular length, what is the value of this L equals to what? That is what we have to calculate. Okay. Now in this case, see how L we can find out here. We have, for finding out the L, we have to find out how much the heat transfer area is required. Isn't it? There are two things. One is how much heat is lost by the mercury, how much heat gained by the water. These are the two things. And in addition to that, how much is the heat transfer between the cold fluid and the hot fluid. That is going to be the same as these two factors. But when we are looking at the how much heat is transferred, there basically the area comes into the picture, which is nothing but the heat transfer area. And this heat transfer area is going to be what? This heat transfer area is going to be whatever the heat transfer area is surrounding this inner pipe. So that is going to be what? Pi dl. So pi and d we know. We can calculate L from there. Okay. So that is what the idea is. So let us look at each of these factors individually.
Sir, could you please repeat?
It will be clear. It will be clear what I'm trying to say. I have just given a brief overview, but as we go ahead, you will understand what I'm trying to say here. Okay. Is it clear?
Okay, sir.
Just wait. It will be clear once we go ahead. Let me just calculate the different factors here. So I will again come back to this point. So first we calculate the inside area. So inside area in this case, cross-sectional area of the inner pipe. Okay. So cross-sectional area of inner pipe. Cross-sectional area of the inner pipe is going to be what? Pi by 4 di square, isn't it? So that becomes 0.0135 square. So this comes around 1.43 into 10 raised to power minus 4 meter square. Okay. Similarly, the cross-sectional area of the annular region, cross-sectional area of annular region. So that is given as pi by 4 into what is the outer diameter in this case? The outer diameter is 0.41 mm. So that becomes 0.041 square minus 0.019 square. Okay. So now 0.041 is clear from where it is coming. Okay, let's go up in the figure. So this 0.041 is the internal diameter of the outer pipe, isn't it? So this is the internal diameter of the outer pipe. Again, what will be the outer diameter of the inner pipe? outer diameter of the inner pipe is going to be 13.5 plus this thickness of this pipe is there, isn't it, which is 2.75 on the up, and on the downside there will be again 2.75. So total this length, the length here, this length is going to be what? This is going to be 19 mm, isn't it? 13.5 plus 2 into 2.75. So 2 into 2.75 becomes 5.5. So if you add 5.5 in 13.5, that becomes 19 mm, isn't it? So this inner diameter here, outer diameter of the inner pipe is going to be 19 mm. So that is why the when we wanted to calculate the cross-sectional area of the annular region, we have to look at what will be the outer diameter of the inner pipe here, isn't it? So that is 19 mm. So that is what I have written here. Okay, so this area comes out to be 1.037 into 10 raised to power minus 3 meter square. Okay, now why we have calculated the area? That is the question you might be having, isn't it? Because we have calculated the area here because we wanted to calculate the Reynolds number. Now we have been given the flow rate is given, mass flow rate we have to calculate. So now what is been given is this mm is given, which is 1500 kg per hour. If you divide it by a cross sectional area, what we are going to get is a mass flow rate in kg per meter square second. So that is nothing but what? That is nothing but velocity into density, isn't it? So in a Reynolds number, we wanted to calculate as dv rho by mu, isn't it? So v and rho, you can directly get it if you divide this mass flow rate by area. Okay, so that is why we have calculated the cross sectional area in the first place. Okay, so now mass flow rate of mercury is going to be G1, that is given as mm dot by area. So that becomes mm is 1500 kg per hour is given. So 3600, that is kg per second, divided by the area. Mercury is flowing through the inner pipe. So what will be the cross sectional area? 1.43 into 10 raised to power minus 4. So this is going to give me, so this is nothing but A1, this is nothing but A2. So here A1 we have to divide here. So that is going to be 2914 kg per meter square second. Okay. Now based on this we can calculate the Reynolds number. Now Reynolds number RE1 is dV rho, isn't it? So V is 1, so we can write as dG1 by mu. We can put all the values here. So diameter is already given, so that is 0.0135 into G1 is 2914 divided by mu. So here see, from the inner pipe what is flowing? Mercury is flowing, isn't it? So this is mu m. So mercury, in case of mercury, the viscosity is not been given, kinematic viscosity is given, and the density is given. If you look at, for mercury, density is given and kinematic viscosity is given. So if you multiply density into kinematic viscosity, that is going to give me the actual viscosity, isn't it? Correct. So that is what is been done here. So mu m is, in this case, is kinematic viscosity, which is given as 8.5 into 10 raised to power minus 8 into its density. So density is 13200. So this comes out to be 350/60. So from this Reynolds number, we are now sure that the flow inside the inner pipe is in a turbulent region, because the Reynolds number is greater than 10,000, isn't it? Now let us calculate again whether the flow is laminar or turbulent in a annular region. So for a annular region, see in a inner pipe, for the flow through the inner pipe, the mass flow rate we have calculated easily, but for the flow through the annular region, the mass flow rate we don't know. Mass flow rate is not known. So I can go back again. Just wait. Okay. So here you can see this 1500 flow rate is given, mass flow rate is given, but here what is the flow rate? What is MW? That is unknown. Here MW dot, this is unknown. This is unknown. So we can calculate M dot W directly by making a heat balance. So whatever the heat lost by the mercury should be the heat gained by the water. And if you make that balance, we can directly calculate MW. Okay, so let us do that. So from the heat balance, so heat lost by the mercury should be the heat gained by the water. So we can write down this as MM CPM into inlet temperature of the mercury, that is 250, minus outlet temperature of mercury, that is 40, and that should be equals to MW dot CPW into inlet. The outlet temperature of the water is 40 degrees Celsius and the inlet is 26. So the only unknown in this case is MW. We can put all the values. So MM is 1500 into CPM is 0.14 into 250 minus 40. So this is equals to Q, isn't it? This is equals to Q. So Q is obtained as, in this case, Q is obtained as, what is the value? 1500 into 0.114 into 250 minus 40. So that becomes 4400 kilojoule. This is in kilojoule, isn't it? Because what is the unit of the kg per, just wait, kg per hour is there. So this is going to be kilojoule per hour, and the
Sir, it will be joule per hour only.
why?
kg is the standard SI unit.
But Cp is given in kilojoule per kg, isn't it? Isn't it? This Cp is given in kilojoule per kg, and this is kg per hour is given.
Okay, sir. Okay.
So this we can equate to MW dot as it is into CPW. CPW is given as 4.2 into 40 minus 26. So from this MW dot can be obtained as 750 kg per hour, isn't it?
Yes, sir.
So now based on this, now we can calculate this mass flow rate we have got, but we wanted to have it in kg per meter square per second. That is what we are interested in, isn't it? Because we wanted to calculate the Reynolds number, isn't it? Now the area we know, isn't it? So we can calculate, in this case we can calculate the G2. G2 in this case is going to be what? MW divided by area into 3600, isn't it? So 750 divided by area, annular region area we have already calculated, A2, that is 1.037 into 10 raised to the power minus 3 into 3600. So this comes around 201 kg per meter square second.
So
Isn't
it's
it?
202.
It's perfectly all right. This last digit could be some changes in that, doesn't matter. Okay, depending on how accurately calculated the area. Okay, so now we wanted to calculate the Reynolds number. So now Reynolds number can be given as, again, dV rho by mu W, isn't it? Correct. That can be written as dG2 by mu W. Now what will be D here? See, the flow is now through the annular region. So there is no a standard pipe, isn't it? It's a annular region. So for annular region, we have to use D as a equivalent diameter, isn't it? So this should be DE. So equivalent diameter DE is defined as what?
Similar that we calculate characteristic length. Is it something similar?
No, it is something like that, but not exactly the characteristic length. In a fluid mechanics, you will get to know this later on somewhere, since your fluid mechanics is going on, isn't it?
Yes, sir.
So whenever we are looking at the flow through the annular region, one has to use the equivalent diameter. The equivalent diameter is defined as 4 into area divided by weighted perimeter. So this is the formula one has to use. This is defined as a equivalent diameter. So 4 into area we already know. Area is 1.037 into 10 raised to power minus 3. And weighted perimeter in this case is going to be what? Is going to be pi di. So that is 4 into 1.037 into 10 raised to power minus 3 divided by 3.14 into di is what? Di is given as, di is the internal diameter, that is 0.019. So this di is going to be, I can go up and explain. In this case, since we are looking at the flow through the annular region, this internal diameter is going to be this diameter here, isn't it? So that is going to be 19 mm. That is going to be 19 mm, isn't it? So that is why 0.019 is used here. Okay, so that is the area which will be corresponding to the weighted perimeter, isn't it? So we can calculate this. This comes around, the equivalent diameter in this case comes around 0.0695 meters. So now we can calculate Reynolds number based on this. So Reynolds number in this case will be 0.0695 into G2 we have already calculated 201, and the viscosity of the water is given, that is 7.3 into 10 raised to power minus 4. So the Reynolds number comes around, Reynolds number 2, this is RE2. Reynolds number 2 comes around 19136. So which is again greater than 10,000, isn't it? So flow is turbulent. Flow is turbulent. Now in both the cases, in case of the flow of mercury through the inner pipe, there also the flow is turbulent. Also for the water which is flowing through the annular region, flow is turbulent in both the cases. Now calculate the heat transfer coefficient for the flow through the inner pipe. Calculate the heat transfer coefficient for the flow through the annular region. So let us calculate for the inner pipe. For inner pipe. So from the inner pipe, what is flowing in the inner pipe? In the inner pipe, the mercury is flowing. So mercury is nothing but the liquid metal. So remember, if you remember your last class, for the liquid metal, we have given the correlation, isn't it? The correlation by Sider and Tate. So SIEDER, Sider, Tate correlation. So Sider-Tate correlation given as Nu is given as 5 plus 0.025 into Piclet number raised to the power 0.8, isn't it? That is what the correlation given by Sider and Tate. So now Piclet number is what? Piclet number is Reynolds number into Prandtl number. Correct. Again, Reynolds number we have already calculated. Reynolds number is 35060, but Prandtl number we have to calculate. So the Prandtl number is Cp mu by K. So we can put all the values. Cp is already given, that is Cp for this case is given. So Cp is given as 0.14. 0.14 is given into 10 raised to power 3 into mu. Mu is not given, but sorry. Mu is not given, but kinematic viscosity and density is given, so we can multiply that. So 13200 into 8.5 into 10 raised to power minus 8. So that is Cp mu, and divided by K. So K is given as 11.5. So Prandtl number comes around. So Prandtl number in this case, okay, just wait. Okay, so Prandtl number comes around 0.0149. Just check whether this value is correct. Just check whether this value is correct. So 0.14 into e raised to power 3 into 13200 into 8.5 into e raised to minus 8 divided by 11.5. This comes around 0.0140. So it's okay. It's perfectly all right. So nearly the same value you are going to get it. Is it correct? Okay. Now we can calculate the Nusselt number from this.
0.0136.
13 is the correct answer. Let me just correct it. Okay. Just let me erase this. 13 is the correct answer. Okay. 0.013. Okay. So now let us calculate Nusselt number, which is nothing but HD by K. HD by K. So that is given as 5 plus 0.025 into Reynolds number, which we have already calculated, that is 35060 into Prandtl number is 0.013 raised to the power 0.8. Just calculate this value. This value comes around 42.3. Just check whether this is correct. And this HD by K is given as, is it correct? This value?
Yes, sir, I'm calculating.
So this will be, since we are looking at the flow through the inner pipe, this will be HI. D in this case, since the diameter which we are using in this case will be a equivalent. In this case, the diameter is going to be the inner diameter again. So that is going to be the inner diameter DI, and K will be mercury. So HI will be given as 42.3 into Km. Km, the thermal conductivity of the mercury is given as 11.5 divided by diameter. So diameter in this case is 0.0135. So this comes around.
Sir, the value is coming very small.
How much is the value?
Number 8.34.
Let me just check. Okay. 35060 into 0.013 raised to the power 0.8 into 0.025 plus 5. just let me check. I have used the expression correct. Just wait. So Nusselt number 0.025. Okay, so it comes around 8, isn't it? So let me just correct it. This comes around
8.349.
8.34. Okay. 8.34. Okay. So let us correct it here also. 8.34. So 8.34. Okay. Now based on this, what is the value of H? What is the value of H?
7112. 7112.
71112.
12.
Okay.
0.30.
Okay, perfectly all right. No problem. 30. Now let us calculate the another factor. Okay, so this is 7,112.3 watt per meter square degree Celsius.
Sir, could you tell what relation did we use to calculate Nusselt number?
This is the relation we have used, Sidertet correlation. Nusselt number is given as 5 plus 0.025 into Peclet number raised to power 0.8.
Sir, I think you've used the wrong expression. I think you've used the wrong expression. The relation which you have used is Saban and Shimazaki. As
The
given
name
in the
might
slide.
be, I might have used the name incorrectly. Just wait. Since it's see, this is the liquid metal, isn't it? So we have to use the expression given by Siban and Shimazaki. Yes, Siban and Shimazaki. Yes, Siban and Shimazaki. Correct. You are absolutely correct. Siban and Shimazaki. This correlation is correct. This name is not correct.
Yes, sir.
That I will correct it. So this is Siban and spelling is SHI or SI?
SHI.
SHI. Okay. Okay, so now let's move to the flow of water. Okay. So now water is flowing through the annular region. Water is flowing through the annular region, and we have already found out that the Reynolds number is a more than 10,000. So clearly we have to use the correlation which is for the turbulent flow, isn't it? So for water, so we have to use the correlation which is Dittus-Boelter equation. Dittus. So that is what we have to use. So that is given as Nusselt number is given as 0.02323. Reynolds number raised to the power 0.8 into Prandtl number raised to the power 0.4. This 0.4 is because we are heating the water. That is why the exponent is 0.4. So we can again put all the values here. So 0.023 into Reynolds number we have already calculated, that is 19136 raised to the power 0.8 into Prandtl number is for the water is given as 4.9, which is already given in the problem statement. This 0.4 is for the heating. So the Nusselt number is calculated here as 115.7. Okay, and this is given as, this will be given as what? H2 dE by KW, isn't it? Because the Reynolds number calculated in terms of the equivalent diameter, therefore this Nusselt number is also represented in terms of the equivalent diameter. So in this case, H2 can be given as 115.7 into Kw. Kw in this case is going to be 0.6115 divided by equivalent diameter is going to be 0.0695. So the H2 comes out to be, anybody?
1023.71.
So I got 1024. So this is correct.
Yes, sir.
Watt per meter square degree Celsius, correct. Now we have to calculate the overall heat transfer coefficient based on this, because we wanted to calculate the heat transfer area, isn't it? So heat transfer area, before that we have to calculate the overall heat transfer coefficient. So let us define the overall heat transfer coefficient in terms of the internal surface area. So that is given as 1 upon Hi plus Di by D naught H naught, isn't it? So the resistance offered by the metal wall we are neglecting, isn't it? So this can be 1 by Hi is the mercury is flowing inside. So that is 7112.3, isn't it? D naught Di is what? Internal diameter. In this case is going to be what? Internal diameter in this case is going to be 0.0135, because we are calculating based on the internal surface area. Outer surface area is going to be, in this case, what will be the outside surface area of this inner tube? Outside surface area of this inner tube is going to be 0.019, isn't it? Into the H naught. So H naught is this. This is the H naught. This is the outer surface area. So this is H naught. Maybe I just rearrange this. So this will be H1 and this will be H2. Okay. So H2 in this case is going to be 1024. Okay. So UI is obtained as, calculate the value of UI. So 7112.3 inverse plus 0.0135 divided by 0.019 divided by 10.
Sir, it's 8.34 into 10 raised to the power minus 4.
And what will be UI? So inverse of that, isn't it?
Okay, sir.
So that becomes 1198.35. Isn't it? Correct. Now we have to calculate the, see, the heat lost by the hot fluid is transferred to the cold fluid, isn't it? And that is given as, in this case, Q is given as UA delta T. So this is UI AI delta T LMTD. Why LMTD? Why LMTD? Because if we go back up here, if you look at here, the temperature difference at one end and the temperature difference at another end is not same. So here at this end, what is the temperature difference? 250 minus 40. At this end, what is the temperature difference? 40 minus 26. So this temperature difference is varying across the length. And in such cases, we have to use the log mean temperature difference. If you remember your last class, we said that, isn't it? Whenever there is a change in the temperature difference across the length of the pipe, in case of double pipe heat exchanger, we have to use the log mean temperature difference. We will derive this later on. But for a time being, in such cases, what we have to use is a log mean temperature difference instead of just a simple temperature difference, isn't it? Okay. So in this case, delta T LMTD we can directly calculate. So delta T1 in this case is going to be 250 minus 40. So that is one thing. And delta T2 is going to be 40 minus 26, isn't it? So delta T LMTD, so this comes around 210 degrees Celsius and this comes around 14 degrees Celsius, isn't it? Delta T LMTD is defined as delta T1 minus delta T2 divided by ln delta T1 by delta T2 So if we put the values here, what we get is delta T LMTD comes around 72.4 degrees Celsius. So I can put it in this equation. So Q we have anyway calculated. So Q comes out to be, if I go back, up, so Q we have already calculated. So Q is 44100 kilojoule per hour. 44100, isn't it? 44,100. So I will just put it everything in this equation. So this becomes 44100 kilojoule per hour is given. So that is 1000. So that is joule per hour is there. So 3600. UI is 1198.35 into A is pi dl. Pi dl internal area is there. So pi di into L into delta T LMTD is 72.4. So we can calculate L here. So that we can calculate L here. So this DI, in this case, DI is going to be 0.0135. Okay. So we can calculate this as 4400 into 1000 divided by 3600. So that is the divided by 1198.35 into 3.14 into 0.0135 into 72.4. So L comes around 3.33. Is it correct? Is it correct?
Yes, sir.
Okay, so let me just correct it. I have made some mistake. So 72112. Okay. Why this is coming? Okay.
So could you
So
show the
this,
calculation again?
I'll just scroll up a little bit.
Yes, sir. Sir, is that 1198.35 or 119835?
1198.35. That is what we have obtained UI.
Yes, sir. Answer is correct.
So 44. Into 10 power 3 3600 into 1198.35. So area in this case comes around let me just calculate 4400 into e raised to power 3 divided by 3600 divided by 1198.35 into 72.4. So that is 0.1411 meter square. Okay. 0.1411. So this comes around 3.33 meter. Okay. So can we stop here? Is it all right?
Yes, sir.
Okay. So we stop here, and this I will upload it. Just let me save this as export. This is a tube number 5. Place it. Yes. Okay. So we stop here and then see you on Monday.
Sir, won't we have a
Unless
class on Thursday?
Thursday. Sorry. I'm really sorry. I just forgot that.